2, 1, go.
Let's start.
It's on.
It's on. Okay. Hello and welcome. Thank you for being here today. We are hosting a special digital future work event titled Light Structure. This topic was inspired by my research work with performance-driven architecture design and structural optimization. I'm Nick Bao. I'm a registered architect in Australia and a lecturer at School of Architecture and Urban Design, IMIT University. And I'm completing my PhD degree in the topic of integrating topology optimization and multi-agent algorithm for architecture design and robotic fabrication at the Center for Innovative Structures and Materials, CISM, and School of Engineering and School of Architecture at IMIT. I gained my Master of Architecture from the University of Melbourne and Bachelor of Architecture from IMIT University. I focus on my research into 3 areas, including intricate architecture and structure form finding, algorithm development, and robotic fabrication. I have embarked on a new journey of architecture engineering technology, and much of my journey was inspired by my supervisors, Professor Mike Shear and Professor Roland Snooks, in the past several years. They encouraged me to seek to uncover new architecture methodology and internal methodology and thoughts instead of the possibilities of the theories and the realities. And I'm exploring internal and external implications of generative design and digital fabrication in the current scene. I would like to thank all my colleagues at IMIT CISM and IMIT Architecture Tectonic Formation Lab. So today we named the topic as Light Structures, which is computational structure design methods for improving architecture design quality. With the development of the computers and the technologies, more and more structural engineers and architects use the various computer-aided approaches to reduce the weight of structure. Lightweight structures, such as membrane structures, shell structures, structure surfaces, computational gridshell system, lightweight truss, topology optimization, and polyhedral structures have become an integral part of the international building scheme. This session brings together a group of world-leading architecture and engineering scholars who are experts on computational architecture and structure design methods to discuss these possibilities of improving architecture design quality during the conceptual stage of the design process. So today the panelists are respectively Masoud Akabazet from the University of Pennsylvania, US, and Pierluigi Di Accanto from TU Munich, German, Caitlin Miller from MIT, US, Alberto Pugnali from the University of Melbourne, and the Professor Mike Shear from IMIT University, Australia. So the first presenter is Masoud Akabazet, who is a designer with a unique academic background and experience in architecture design, computation, and the structural engineer. He is the assistant professor of architecture in structure and advanced technologies and the director of the Polyhedral Structure Lab at the UPenn. He holds a doctorate degree from the Institute of Technology in Architecture, ETH, Zurich. He holds 2 degrees from MIT, Master of Architecture Study Computational, and a Master of Architecture. He also has other master degrees in earthquake engineering and dynamic of structure and bachelor degree in civil engineering. His main research topic is 3D-dimensional graphics, statics, structure and architecture design and technology. In 2020, he has received the National Science Foundation Career Award to extend the methods of 3D polyhedral graphics, statics for education, design and optimization of high-performance structure. So let's welcome Masoon to present his work.
Thank you very much, Nick, for a very generous introduction. It's always it's a little bit humbling to hear that you have to go through all those degrees in the introduction of my name. I have to shorten that probably in my website. So yes, thank you very much again for the invitation. Just allow me to share my screen. All right. Okay. Is it running? Okay. Right. Sorry, it seems that there is a little bit of glitch. Cool. Thank you again for the invitation. It's a great pleasure to present some of our research in this gathering, and I'm very honored to be among very prestigious researchers and professors, colleagues, and mentors in this gathering. So I named the presentation, my presentation today is Strength, Lightweightness, and Efficiency. And to basically tweak it a little bit with respect to the topic of the lighter structures. Yes, my name is Vasilij Barzadeh, and I'm the Director of Polyhedral Structures Lab at the Weizmann School of Design, University of Pennsylvania. I'll start with an image from nature. Structures in nature have always been the source of inspiration for...
We can't see your screen.
Yeah, we can't see your screen.
Oh, sorry. It was not shared. Okay. Sorry about that. Okay. All right. Good. So structures in nature have always been a source of inspirations for engineers and designers in developing efficient structural systems. In 1867, George Hermann von Meyer showed that the structure of bones is composed of a delicate lattice work of tiny interlaced trabeculae, crossing each other as nearly as possible to orthogonal. Kuhlmann, at the time, was developing the methods of graphic statics at ETH Zurich. He met von Meyer at the gathering of the Society for Natural Sciences in Zurich in July 1866. And von Meyer particularly highlighted his interaction with Kuhlmann in 1867 publications. So what is the result of this interaction? Is that Kuhlmann adopted this idea and described the bonus structure as the diagram of the lines of the stress in both tension and compression. And it is designed his famous crane by using graphical methods accordingly. The main objective possibly was to design and optimize a structural system. And by optimize, it can be interpreted that the internal geometry of the structure follows the stress patterns within the system. The alignment of geometry and the flow of forces has long been investigated using the hanging chain models proposed by Robert Hooke, but the geometry-based approach made it much easier for many designers to find the structural forms where the form follows the internal stress. Although this method originally existed as a 2D method, the intuitive aspect of the method made it quite popular among many designers and master builders in the design of three-dimensional structures. To mention a few, Antoni Gaudi, Rafael Guastavino, Pierluigi Nervi, and Robert Meillard, they all used these two-dimensional graphical methods for the design of their three-dimensional structures. In 2016, I was blessed to be among a few who extended the methods to 3D, which is called 3D or polyhedral graphical statics, where the equilibrium of forces is represented by closed polyhedral cells with planar faces. At the time, and even today, there were many doubts about the application of these methods. In fact, it was argued that constraints of these methods to polyhedral diagrams makes it challenging to describe equilibrium for non-polyhedral systems. Even Maxwell, in his groundbreaking paper in 1864, alludes to the complexity of using these diagrams in describing some equilibrium states. In 2017, when I just established Polyhedral Structures Lab at the Weizmann School of Design, it was all about accepting the existing constraints and considering that as the mission statement for the research. Since 2017, we have applied this method to a variety of design examples and explored the extension of this method further. For the past 4 years, basically, we explored a wide range of examples and problems. We have extended the theoretical backbone of the method, applied the methods in various scales, testing the application of the method in design of cellular solids in microscales, developed design softwares, an educational platform, analyzing natural structures, and finally applying the methods to the future of manufacturing. Unfortunately, we don't have time to go through all these examples. I've selected a few, and I'm going to highlight certain lessons that we learned through all these exercises. To begin with, I would start with a very simple and a small example that was a cast-in-place funicular polyhedral concrete. The size of the sample is quite small. It's actually 60 centimeter in height and 30 centimeter in depth or diameter. And it was inspired by the famous concrete sample example by ACI, American Concrete Institute. What we showed in this example was that the 12 kilogram sample designed using the methods of polyhedral graphic statics could take up to 24,000 of load, 24,000 kilogram load, which is equivalent of 245 kilonewton. So what are the lessons that we learned here? That the funicular system can have internal geometric indeterminacies, which makes the system resilient compared to a single layered funicular system. That means that if one of the members buckles, still the system would actually transfer the load significantly to withstand the external loads. The notion of constant distress in the system can be very well explained by the explosion of all parts at the moment of the failure. And of course, the weight, the load bearing with respect to the weight ratio is quite high, which shows the efficiency and lightweightness of such structures. We took this example to a larger scale. And in this exercise, which is called Hedrocrete, we investigated the application of this method in design of larger scale, lightweight infrastructural projects like the one that you see. So this spatial system is quite unique because the bottom chord of the system is in pure tension and the top chord is in pure compression, the top chord is in tension. And the self-weight of the top chord is actually used to keep the bottom members in compression as a self-standing and self-supporting structural form. So you can see that the maximum span is 540 meters, and the total bounding box of the structure is about 10.80 meters by 9.30. So what did we learn from this exercise? This was also quite interesting. So the total volume of concrete was 3.5 cubic meter, distributed in 50 cubic meter of space. And the load-bearing capacity of the structure was calculated at 1,000 kilonewton. We tried to build and design, not building, obviously, design and basically analyze a structural system with the same spanning ratio using a conventional post-Beam methods of concrete. So the volume 3.5 meter cubic square meter, it was used to basically span the same area, but the total load-bearing capacity was calculated as 82 kilonewton. In fact, we tried to match that load-bearing capacity with the same volume of concrete, and we realized that we need 330% more concrete and 10% more rebars, which clearly shows the efficiency of the system in scaling up these structures in larger scale, right, an application. The next exercise is a composite system. And in this exercise, basically, we try to address some of the limitations of assembly in the previous larger scale system, as well as the equilibrium states, right? So this is obviously built in a form of a furniture, particularly because we wanted to use the possibility of assembly and disassembly of a technique for different occasions and show how this method can be applied for larger scale systems that are built offsite and then brought back to the inside in different locations and put together. So yes, the equilibrium of form can be described using polyhedral system by a closed polyhedral cell, but that means that there are also cases that basically the equilibrium can be explored by complex force cells or self-intersecting phases, right? So this was not explored very well in the literature. So we took this as, again, as a mission to show how we can control these complex force distributions. So for this reason, we developed a quadratic definition of the problem to control the areas for self-intersecting faces. And then we were able not only to control the area, but make certain applied loads disappear from the definition of the problem. So as a result, we were able to create distribution of forces that we had really well control over the boundary condition and how to basically remove certain horizontal forces in the boundary condition using geometric techniques, right? Beside that, we came up with a new method of assembly because usually in the assembly of a spatial systems, the sequence of assembly becomes quite important. So we eliminated the linear members connecting the nodes, and we directly went for the node-based assembly for funicular structures. But for that node-based assembly, obviously the collision becomes a problem. And for that reason, we developed a locking mechanism that as long as two member is available for assembly, the member that the node could be assembled without any particular sequence during the construction. And in the meantime, basically the detailing allowed us to withstand certain tensile forces in the members during the assembly and afterwards. So this is basically the result of that construction. Moving to another example, and particularly this example is the celebration of the constraints of polyhedral constraints in the construction of lightweight structures. And this is an ongoing research that's a collaboration between UPenn, Villanova University, Technical University of Darmstadt, and City College, New York. And in this example, yes, because of the polyhedral constraints, we developed a multi-layer funicular system as a bridge that is going to be made out of multi-layer glass. So particularly unlike many other funicular designs that the self-weight is used as the applied load, here we tried to minimize the self-weight by using hollow glass units as a building block for the construction of the bridge. So the initial basically preliminary analysis showed the feasibility of this work, but obviously we had to move on and investigate the behavior of a single construction module. So in this example, you see that this cell, which is going to be used as the construction module of the bridge, is made out of 1 centimeter float glass, which is equivalent of the same window glass that we have in the buildings, right? Just to show the possibility of working with really cheap and accessible materials, right? So we built this sample, and the load-bearing capacity of the sample was about, as you see, so that's actually in pounds. It's more or less about like 40,000 pounds or 37,000 pounds with different samples. So it clearly showed that yes, it is feasible to build such efficient lightweight structure out of glass, and if we can control glass as one of the most challenging construction materials. To build such system and rethink the conventional detailing, obviously we can extend the use of these materials to other sheet-based systems. And therefore we can create a variety of different lightweight systems, but high performance, right? Currently, we are investigating the detailing, particular detailing had to be developed for that system. So we are looking into the cast pieces for the side plates to interlock with each other, again, to rethink and basically have an innovation in the detailing of glass, all glass structural system. And yes, this is the work of one of my PhD students, Yao Lu, and we will talk more about this. Unfortunately, I can't share with you more, but this is just a glance of an upcoming research. There is an ongoing research also on the application of this method in the design of a particular spatial cellular systems that is called cellular structures. This is another work of my PhD student, Mustafa Akbari, who actually extended the typology of funicular system to cellular system, again, based on polyhedral diagram. So regularly in a cellular system, we rely significantly on the buckling performance, but with particular design techniques, you're able to translate cellular structure to cellular structure, that you go from n-manifold geometry to 2-manifold. That makes it even easier to construct. So again, the preliminary studies showed that, yes, the structure, actually the load-bearing capacity of the structure increases, the constructability of the structure would become basically facilitated a lot. And obviously you can see that variety of different typology of structures would actually emerge as a result of using this technique, particularly for architectural purposes. And the interesting thing is that the method can also be applied to the design of cellular solids. So this is again an ongoing work. I can't go into a lot of detail, just to give you a glance that this is a collaboration with McGill University, that we are looking into the possibility of using graphical methods and polyhedral graphic statics in the design of cellular solids, and how the subdivision can actually tweak the property of the material from a stretching dominant structure to bending dominant, and vice versa. So this is, again, very exciting for us to see the application in microscale. So to close the loop, I'll get back to the natural examples, natural structures. Obviously, nature has learned its lesson really well, how to use material where it's needed, where the stresses actually exist, and always tries to create lightweight but high performance systems, right? So there's another research and ongoing investigation by another PhD student of mine, Hao Zheng, who is looking into the wings of dragonflies as one of the most lightweight structures that we can find in nature, right? So the interesting pattern in the wings of the dragonfly inspired us to look at that and analyze that using the methods of graphic statics to see whether natural structures can be described with this simplified methods, right? So he extracted the force diagram from the internal network of the wing and tried to reconstruct the wings and compare the force distribution in the members and the thickness in the actual structure with the structures that are generated using graphic statics. And surprisingly, the dimensions match really, really well, which shows that certainly these phenomena can be described using graphical methods, although it might seem as simplified methods of design. But interestingly, this would actually help us to understand all these, I would say, invisible forces and boundary conditions that these structures have been evolved to become optimized for those. And we would be able to identify such forces using graphical methods. Just to give you a little bit of projection to the future, we are intending to build a basically educational platform supported by the National Science Foundation for practitioners and obviously students and researchers. This has not been released yet, but in a month or so, you should expect that this would be released from us. This is another work of my coming PhD student, Hua Chai. And to just conclude all the discussion is that we recently had a chance, and I was lucky to be part of a team to receive a grant from Future Manufacturing sector of National Science Foundation to use the methods of graphic statics and basically apply that to the future of construction. Unfortunately, I can't basically show a lot about this, just to let you know that this planarity and this constraint that many people had doubts about it now can be applied to the design of efficient structures for future. This is, by the way, again, another work of my PhD student, Mustafa Akbari. And with this, I just wanted to conclude my talk and basically open the discussion for the rest of the panelists and listen to the other talks. Thank you very much.
Thank you, Masoud, for the amazing presentation. Okay, let's move to the next presenter. Is Pierluigi De Canto, who graduated in the building engineering architecture from the University of Pisa in 2007, and gained professional experience in various architecture and engineering offices. In 2012, he received the Master of Architecture degree from the Architecture Association in UK, and in 2018, he got a PhD from ETH Zurich. After working as a postdoc at ETH Zurich and as a director of XMate, in 2021, he was appointed to the assistant professor of structural design at TU Munich. His research explores the convergence of architecture and structural engineering through computational design and emergency construction technologies. So let's welcome Dr. Pierluigi start his talk.
Thank you very much. Just a second that I share my screen. Here it is. Can you see it? Yeah. So, yeah. Well, thank you very much for the very warm welcome. And for me, it's a great honor to be here with such a very prominent panel of colleagues, lecturers, and friends that are joining me today. Said my name is Pierluigi Da Cunto. I'm currently assistant professor of structural design at the Technical University of Munich. But in fact, I just moved to TUM just a few months ago. And before I was at the chair of structural design at ETH Zurich under the supervision of Professor Josef Schwarz. So my talk today is about the design of lightweight structure using vector-based graphic statics. Actually, we just as this amazing presentation by Masoud also about graphic statics. I'm very happy to be talking right after him and going on discussing about the fantastic possibilities as graphic statics is giving to structural design. Well, when it comes to the topic of structural design, as you know, clearly what is very relevant is the relationship between form and forces, which is very much expressed by the principle of resistance through form. So it is indeed only when a structural form is designed in relation to the distribution of its internal forces that is really possible to make effective use of the material resources, and as such reduce the amount of building materials and indeed also the embodied carbon of the structures that we design. In this regard, the Salginato Bell Bridge in Switzerland by Robert Maillard, that was shown also by Masoud in the presentation before, is actually one of the most incredible examples of the elegance that can be achieved by designing following the principle of resistance through form. The form of this bridge indeed is directly related to the distribution of its internal forces. It is interesting to see that Robert Maillard made actually extensive use of graphical methods for structural engineering and in particular graphic statics for the design of this bridge. Graphic statics, we heard already before, has been developed in the 19th century as a series of geometric constructions that correlate the form of a structure to the distribution of its internal forces. And it is based on two main diagrams, the form diagram and the force diagrams. As we see here, the form diagram represents the geometric layout of a loaded structure with all the forces applied to it, while the force diagram represents the equilibrium of the forces within this structure. This series of geometric constructions were developed mostly at the end of the 19th century by Carl Kuhlmann, Luigi Cremona, for example, and James Clerk Maxwell. Now, thanks to the developments of the new digital tools in the last few years, an impressive amount of research has been carried out in the field of graphic statics, but specifically on its extension to the third dimension and its implementation into computational tools for structural design. Specifically, for a given 3D form diagram, as we see in the slides on the left is a self-stressed tetrahedron, it is generally possible to define two different types of force diagrams in 3D, the polyhedral-based force diagram and the vector-based. In the polyhedron-based approach, the equilibrium of each node of the form diagram is represented by a polyhedral cell. Actually, Masoud very much explained this because it was the very first one that started a journey into the exploration of the polyhedron-based force diagram and in general force polyhedron-based graphic statics in 3D. In my case, I rather focus more on the vector-based approach. In this case, the equilibrium of each node of the structure is represented by a closed cycle of force vector, also known as force polygons. I've been developing this work and I'm still working on it, thanks also to the collaboration of many colleagues at ETH Zurich, at EPFL Lausanne, and UC Louvain. So going a bit more in depth into this, for a structure in static equilibrium regarded as a form diagram, F, like this self-stressed tetrahedron, a vector-based force diagram can be built node by nodes. And like in traditional 2D graphic statics, we can generate for each node of the structure some closed cycles of force vector, or also known force polygons. These force polygons can be then assembled all together into one unique force diagram. In the general case, in vector-based graphic statics, especially in 3D, there is not just one specific configuration of the force diagram, and this is due to certain topological property of the underlying graph of the form diagram. Well, by taking advantage of the recent development in digital tools and computational tools, it has been possible to implement all these constructions into computational tools that can be used for manipulating form and forces at the same time. For example, in this case, we are about to release a Grasshopper plugin for this vector-based graphic statics that allows to work with form and forces at the same time. Like we see here again, the self-stressed tetrahedron, it's possible to transform a force diagram and assess the consequence transformation on the form diagram and vice versa. Basically, this becomes very relevant when it comes to the actual structural design, like in the case of this bridge here, in which form and forces are controlled at the same time. Or for example, in this case of a suspension bridge, in which we can also introduce specific constraints. For example, we see how form and forces are transformed in placing the constraint that we want, for example, that all the forces within the suspension cable are the same. But it is very clearly evident in the force diagram, since all the corresponding edges have the same length. That means the same force magnitude. With the combinatorial equilibrium modeling that has been developed by my colleague Ole Olbrook, and I've been collaborating with him for the implementation of this into computational tools, it has been possible to introduce a third diagram on top of the form and the force diagram, and this is the topological diagram. And thanks to this topological diagram, it is possible to operate at the level of the topology of a structure, and as such, changing the connectivity of the constituting element. For each topology, then it is possible to work on the metric variations. This allows to start, for example, with the same topological diagram, so the same ground topology of a structure, and generates multiple variations of forms that are in static equilibrium. Also, in this case, this has been implemented into a computational tool that allow to operate the structural design and constraint transformations of structures. For example, in this case, we see how to minimize the load path of the structure, which is a property proportional of the self-weight of the structure itself. And again, also in this case, it is possible to make the form finding of structure, but at the same time imposing constraints both on the form and the forces. This is particularly relevant when it comes to the design of lightweight, large span roof structures, for example, but also at the level of architectural design. For example, in this case, we apply the very same approaches for the construction of a grids that is supporting these different levels of a building. The great possibilities offered by graphic statics and this working with combinatorial variation is indeed the possibility to go beyond the conventional structural typologies. So, for example, we see here going beyond the conventional approach of the column slabs and generating different variations for the problem of structures for a building. In research work, I've been collaborating with the chair of digital architectonics at the ETH Zurich, and we explored the possibility to combine this generative tool like vector-based graphic statics and the combinatorial equilibrium modeling with machine learning algorithms. And this with the aim to leverage the power of the machine to support the designer in the structural design process. In fact, when we use tools like the combinatorial equilibrium modeling or vector-based graphic statics, it is possible to produce very quickly multidimensional design spaces of solutions that in this the human designer cannot really handle very easily. In this regard, the handling of these complex design spaces has been tackled with the use of machine learning. For example, with techniques for clustering, like the self-organizing maps. In this technique, basically, a multidimensional design space is converted into a bidimensional map in which then the human designer can very easily navigate, and as such, being able to distinguish different families of different structures and, for example, make a selection among the preferred and non-preferred options. A very interesting point is that based on this selection and classification, this can be used as an input again for the machine in order to learn the correlation between input and outputs according to the preference of the human designer. And for example, then supports the designer in generating new design options that most likely the designer would like, and eventually make a final selection according to both quantitative and qualitative criteria. So in the use of these machine learning algorithms allow to bring into design process also qualitative criteria. This eventually ends up to the final selection of a specific design solution. In the last few years, I had the chance to test the relationship between form and forces in several projects within real design scenarios. And design developments of these projects actually relies very much on the use of vector-based graphic statics and all the tools that I presented before. Here, I will show just a selection of some projects that deal with different structural behaviors, different scales, and different materials. For example, in this project, the fold desk, the aim was to create a novel table typology as a combination of two elements, a tabletop and a whiteboard. The geometry of this table has been defined using a novel design method for structural folding in architecture, And this method was based on the use of a tetrahedral grid in order to generate the topology of the structure and also the geometry of a rigid folded plate structure. And then vector-based graphic statics has been used in order to define the geometry of the table by imposing constraints, for example, minimizing the internal forces. Based on this process, then the table has been eventually materialized in a full-scale prototype using 3 millimeter thick steel plates. In this other project of the bending active tensile facades, that is very much related to the design of a structure based on bending active using graphic statics as developed by my colleague Lea Bullig, we tried to retrofit one of the buildings of ETH Zurich with a sun shading facade. So in this case, the project was driven by information related by solar radiation and lighting analysis, but at the same time also forces and material property using graphic statics. And eventually this has been materialized into 1-2 prototype. Very recently, I've been involved in supporting another project for a pavilion by the MIS ETH DFAB group of students, and specifically with the chair of digital building technology at ETH Zurich. And this was for the structural design of this pavilion, the digital bamboo pavilion, in which the structure is generated made of bamboo poles connected with 3D printed nodes. We supported the design by introducing a post-tensioning system that was designed using graphic statics, both at the level of the global structural behavior, but also the level of the connections. These are examples of the connections 3D printed with nylon, and specifically this one here with stainless steel. As we see some pictures and impression of the pavilion. The same technique have been applied to actual projects. These projects by Burgos Garrido Arquitectos, supported by the structural engineer Bernabeu Ingenieros. And specifically, me and a colleague at ETH Zurich have been asked to support the structural form finding of this project. So we use the vector-based graphic statics and the combinatorial equilibrium modeling in order to generate different design solutions that eventually then led us to select a specific solution and then develop it further on with other tools, for example, to test dynamic behaviors and other considerations that clearly cannot be considered using only graphic statics. I conclude my presentation with this project here. It's a proposal for a new stadium in Tokyo for the Olympics in Tokyo. And this was part of a competition that was launched by the ISS in 2016. I took part in it with colleagues at ETH Zurich. And we designed this tensegrity system in which the stands of the stadium are actually supported by this cable nest. And again, the principle is quite simple, using a cable system that is in tension. This is stabilized with columns in compression, but in our project, the columns become the actual stands of the stadium. Then repeating the same operation and stacking on top of each other the different stands of the stadium, it is possible to generate the final design of the stadium, as we did, again, using form and forces at the same time to control and to try to minimize the amount of material. This is a 3D model, and these are some impression of the projects from the outside and also from the inside. So this to conclude my presentation. Again, the power of graphic statics allows to correlate form and forces in structure and go beyond the conventional structural topology and to design completely new structural system. Thank you very much.
Thank you, Pierluigi, and yeah, fantastic presentation. It's very impressive. Okay, so we can move to the discussion later. So the next presenter is Catherine Miller. She is a researcher and educator who works at creative interface of architecture and structural engineering. She is currently an associate professor at MIT in the Department of Architecture with a joint appointment with Civil Environmental Engineering. She is based in the Building Technology program where she leads the Digital Structure Research Group. Her research focuses on empowering the design and the materialization of innovative, creative, sustainable, and high-performance architecture structure through computational algorithms and tools. Professor Miller got a PhD degree in building technology from MIT and a master in computational computational design and optimization from MIT and master degree in structural engineering from Stanford University and a bachelor degree in architecture from MIT and has practiced at several architecture and engineering firms across the US. So let's welcome Professor Miller start her presentation.
Thank you, Nick, for the invitation and for that kind introduction. And hello to my other panelists. It's delightful to be here with all of you today. So for my talk, I named it Computing for Lightness, which perhaps could be the title of all of our talks. But I'll try to describe what I mean specifically throughout my talk. As Nick said, I lead a research group at MIT called Digital Structures. And so the work that I'll show you today is really the work of all of us collaboratively. My group includes people with architecture backgrounds, structural engineering backgrounds, also mathematics, mechanical engineering, computer science. And I really feel that it's the intersection of all of these fields that really is fertile ground for important research in the built environment. And that's the way that we work in a very interdisciplinary and collaborative way. I also wanted to start with this idea of lightness, which I think is a beautiful title for our event today, but also is in some ways a very old concept since before most of us were born. Really the golden age of lightness in structural design and architecture was in the 1960s, as shown by this graph by René Sarger. And really in some way we've actually left this era. After this 1960s excitement about structural lightness, new ideas came about in architecture. Postmodernism came about, and we really left this world of lightness in search of other ideas and other design methods. And I think that's something that we're now considering returning to, and I am very much in favor of that. Perhaps one reason that we left the world of lightness originally was a worry about uniformity or all of design converging to a single answer. Pier Luigi Nervi addressed that when he was practicing. He said, "One must not fear that the adoption of forms and volumes closely following natural laws must lead to a monotonous and unsupportable uniformity of products." Another way to say that is to just look at structures from around the world and across history that embody these ideals of lightness, and to really celebrate the diversity of these structures, as we'll see also today in all of the presentations. There's not just one way to use ideas of lightness or efficiency in design. In many ways, it's actually a way to open up new ideas and to expand the formal palette of architecture. So for me, that's very important, that we're not necessarily all talking about a convergence to a single optimal solution, but we're encouraging an expansion of the ways that we can express ourselves as architects and designers. I also think the principles of lightness are critical for us to consider today because of the effects that buildings have on climate change. You all know that buildings contribute 40% of global greenhouse gas emissions, and there's vast variety in the way that buildings perform, in the amount of energy that they use to operate, but also in the energy and emissions associated with materials and construction, the embodied energy and embodied carbon. In this example from my colleagues John Oxendorf and Catherine Wolf, they found that the Beijing Olympic Stadium on the left uses 14 times the embodied carbon per seat compared to the London Olympic Stadium on the right. Not 14% more, 14 times more. That is a dramatic difference in performance that we would not see in any other engineering discipline. And it's been allowed to proliferate in architecture for a long time because performance hasn't always been part of the equation. But I think given today's context, we really need to consider performance in design, ideally early in the design stage, and we need better tools and methods to do this. When I say early in the design stage, I mean at the time where really big decisions about a building or a structure are made. In this rather simple example, even the decision of the column grid has a huge impact on performance in each of these graphs. The y-axis represents the primary spacing of columns. The x-axis is the secondary spacing. And you can see the very large differences in embodied carbon and structural materials associated with that decision, which is often not even made with a structural engineer present. So how do we do better? How do we start to understand performance while also enabling freedom and creativity and diversity in design? One of the ways that I like to do that is with something called the design space, which is a formal linking between design decisions, usually about geometry, and the performance implications of them. In this really simple design space for a truss supporting a central point load, I could parameterize it by moving the lower left node up and down and left and right. And you can see that the amount of material required to support the load varies in response. This landscape is the design space. Since before I was born, there have been methods developed that can efficiently find the optimal solutions in this design space. Here they are. There's a global optimum and a local optimum. And these methods are very powerful, but they're rarely used in the design of buildings, especially in the large scale conceptual design. And I would argue that part of the reason for that is because it's really hard to formulate an objective function that matters, that describes all of architecture, that describes everything we care about when we're designing a building. We can certainly quantify the amount of material used, which, as I've said, is really important, but we can't characterize very easily or numerically things like culture, context, human experience, the central parts of architectural design and the experience of the built environment. So one way that I like to think about this is that we don't need to throw away the idea of the formal design space or optimization, but we can relax on the idea of the objective function or the idea that we'll find a single optimal solution. So just by looking at this design space a little further beyond these 2 points, we see that it's actually a really fertile landscape full of lots of interesting ideas, most of which are normally discarded in an automated process. But if we can unlock those and start to explore them intentionally while imposing our ideas as a human designer, we can start to find new ideas that perform well and embody our creative intentions. So I work on building tools and methods to enable this type of exploration. I call it design space exploration. This is a tool that I built during my PhD called Structure Fit that explores the shapes of 3-dimensional trusses. The number beneath each design is a measure of performance. It measures the amount of material required. A lower number is better. It's normalized by the original design. And it uses something called an interactive evolutionary algorithm, where the designer is shown a subset of high-performing design ideas generated by the computer. And then he or she selects the ones that are most interesting for qualitative reasons. And those are used to generate new design ideas. In this tool, I also am involved something called direct manipulation, which I think is really important. In any methods that are automated, it's always really important to give the human final control and final say in the design, so it doesn't feel like you're being given an answer. It's really something you're participating in or collaborating in. And tools like this can produce a really, to me, exciting and diverse range of possible solutions that are high performing. So the ones on the left are the geometrically regular ones. Those are the ones that we might have started with. The ones on the right are solutions to optimization algorithms and have been found analytically throughout history by amazing engineers. I'm also interested, however, in the ones in the middle. These are not the solutions to any optimization problem that I can think of, but they're really interesting. They perform better than the initial ideas, in some cases significantly better. And they might represent the best balance of qualitative and quantitative goals in design. And these types of design space exploration tools can help us discover them. What happens if we expand this concept into larger, more realistic scale problems? For example, this large scale truss. We could parameterize this by representing the top and bottom surface of the truss with NURB surfaces that have control points that become variables. Suddenly, I can generate lots and lots of interesting options, too many options. If I have 36 design variables and I want to understand this design space and explore it, my problem becomes I have too many options to explore, actually. So here I'm looking at this very, very tiny percentage of the overall space. It's really hard to make sense of it. And it's really hard to figure out what I want to look at. Even if I have performance, which will take a long time to analyze this many options, it's still hard for me to understand which designs I should be interested in. So a lot of my work recently has focused on these challenges and the related opportunities. That simulations are really useful in early stage design, but a lot of times they're too slow or too reductive. We need approaches between full design space enumeration, like what I just showed, and single solution optimization. We need to find ways to encourage this balance. And we don't want a fully automated design process. That's really a non-starter in architectural design for a variety of practical and conceptual reasons. At the same time, designers are becoming more comfortable using computation in design processes, as we're seeing more and more each year. There's a lot of data that's available. And there are also new methods that are evolving in machine learning that can make use of that data and enable creative processes. One of the simplest examples of this is something called surrogate modeling, which tries to address the problem of slow response time from a computer in a design task where you'd like to be as fast and interactive as possible. And it's a supervised learning method that uses a little bit of training data to generate an approximation model of the relationship between design variables and performance that can then be sampled instantaneously to allow things like real-time exploration of shell structures with full displacement information provided in real time as we sculpt the shell. So instead of sending this structure to a different program or to a different person to analyze to get a response in minutes or hours or days, we get real-time information that allows us to really act creatively and be in a creative flow with instant information as we need it. We've extended this idea. We don't only need to predict single performance metrics or performance fields. We can even start to predict things like the optimal distribution of material in a surface. So I'm sure we'll hear a lot more about this from Mike in a few minutes, but this is the result of a topology optimization on a shell. And here we're using a surrogate model, using something called a graph convolutional neural network to predict the optimal solution. And we can actually do really well with this. And the nice thing about this is that we get a pretty good estimate of where the material needs to be and a really, really fast rate. So this is 165 times faster than the response that the full optimization takes, but we get this result in real time. And so again, it can become an agent in the design process rather than just an analysis at the end. So as we're sculpting this shell, we're seeing in real time, how should the material be distributed optimally if this is the shape of the shell. We can then use that to inform a materialization strategy, either literally taking the topology optimization result, or even using that to inform some other kind of materialization strategy, such as like a waffle structure-like thing where the sizes of the voids are taken from the result of the topology optimization. The surrogate model allows a collapsing of a traditional process that normally takes days or weeks, conceptual design all the way through materialization. Now we can understand this entire process instantaneously, which allows for a lot more exploration and interaction, and helps us find solutions and test solutions in ways we never could before. So we're really excited about surrogate modeling as a way to make compact, portable, and instantaneous performance information available to designers early and creatively. There are several challenges with surrogate models, namely that they require a lot of data to train. So one of the things that I won't show here, but that's ongoing work, is thinking about how to train surrogate models really flexibly with, for example, non-parametrically generated data, and thinking about ways to generalize them across different model types using something called transfer learning. So once we have this instantaneous feedback, how can we use it to organize and orient design space exploration? A simple idea that we have often used in our work is something called clustering. So if I have this enormous space of design alternatives, I can start to use things like unsupervised learning to find relationships or groups. So I start to understand hierarchy and organization in the space. But what we're really interested in is how these design alternatives relate to performance. And we have this problem where in all of these methods, we need to start with design variables. We need some kind of parameterization of the design problem, which arguably is really unnatural and tedious to set up, even for people who really love parametric design. What we would really like, instead of working directly with these design parameters, we'd love to work directly on our objectives. We'd really love to be able to say, hey, can I make the structure a little bit lighter or increase the amount of daylighting a little bit in the space? That's an inverse modeling problem. We can't directly solve that, but we can start to learn correlations between variables and performance objectives and use those to synthesize new, smarter variables automatically that give a lot of control to a designer, but also start to point in directions of high performance. So here we're taking a truss that originally had something like 20 variables, and we can find the 3 key synthetic variables using principal component analysis that align with different performance objectives that we care about. And this simplifies the problem, but also makes it more meaningful for us. More recently, we've been exploring a similar idea using a method that's nonlinear in terms of its mapping between the high dimensional variable space and the low dimensional design space, something called a variational autoencoder, which is similar to the self-organizing maps in some way that Pierluigi showed, with the difference that it's a generative method. So our low-dimensional space that we're able to produce, often we try to produce two-dimensional spaces, can then be projected back to the original variable space so it can directly be used to generate new designs. And so we recently published a paper where we use something called a performance conditioned variational autoencoder, which means that this two-dimensional latent space, this compression of the original 36 variables, also only contains designs that are likely to be high performing. So we end up with a really interesting map, again, a two-dimensional design space, but that represents a lot more geometric variety and complexity, and is guaranteed to find designs that use very little material while offering a lot of choice and flexibility. The performance conditioning is really powerful because that's another level of choice that a designer is given, where if they choose a different performance conditioning value, they can get different types of landscapes that have different types of geometric diversity and variety with different trade-offs in performance. So if we care less about performance, we can find even more interesting and more varied design options, or if we care more, we would perhaps choose the option on the left. So going back to this original map of kind of a jumbled map of way too many options that we don't understand, suddenly we now have this fairly well-organized space, and we can start to identify designs that are high performing. We can also connect this with the idea of surrogate modeling that I mentioned earlier. This is that same example with the instantaneous prediction of the topology optimization result. This was originally an 8-variable problem. We've projected it into a 2-dimensional design space, a latent design space. And again, these spaces that are 2-dimensional are really natural for a human to explore. This white line is kind of a curving path of exploration that someone might have, and they're able to get this instantaneous performance information and also materialization ideas directly driven by topology optimization. So we think these latent performance landscapes are really powerful as a way to create intuitive interfaces for problems that are normally too complex for humans to engage with in a systematic but creative way. So we're currently working on how these ideas can get translated to experts, or sorry, to non-machine learning experts, because there's currently still quite a lot of stuff under the hood that is hard to disseminate. And we're also really interested in thinking about how this works on multi-objective problems, which almost all design problems in the built environment are. And so finally, I wanted to talk about a last research direction, which is also about interfaces and the human design process. How do we inject human intentionality into these processes even more? And so this is an ongoing project funded by the National Science Foundation that we sometimes call Machine Learning for Human Design. And it relates to the idea of the sketch as one of the most powerful analog design methods that persists today. We've seen sketches throughout the other presentations so far, and I'm sure we'll see more. No matter how much automation and digital power we have, there's something really open-ended and freeing about drawing on a piece of paper. So we're asking, can we connect this incredibly powerful means of expression with the power of a systematic design space in terms of performance prediction capabilities and the ability to suggest new ideas based on our inputs? And so we're doing that using machine learning methods. Again, I won't go into a lot of detail about how this works, but one of the ideas is, given 2 sketch ideas, perhaps 2 different team members or one person has 2 ideas, can we take a sketch, get the performance, and we've been able to show that we can predict performance pretty well from sketches at this point, and then also use ideas like interpolation to discover new design ideas that are in between the 2 design concepts. We're working on interpolation methods that are performance driven so that we can generate new design ideas that also improve performance, kind of like what I showed originally with structure fit. We're working on disseminating these ideas also through teaching. My colleague Renaud Deneuve and I developed a class at MIT a few years ago called Creative Machine Learning for Design. And we're currently working on making that into a MOOC on the MIT X and edX platform, which we hope will launch in September. So I hope some of you are able to join us for that. We also have a number of open source tools that are free for you to use in Rhino and Grasshopper that you can access here. And finally, just as some examples of how we apply these ideas in particular projects and material systems, we've been able to show, for example, using these methods that we can reduce the amount of embodied energy in concrete floor systems by up to 75%. Similarly, we're applying these ideas to timber systems where we can both expressively shape and significantly reduce the cost of mass timber. And we're also connecting these to questions of modern fabrication. How can new advances in robotic assembly, for example, connect to efficient and lightweight design? Can these methods of, for example, here we're automating the toolpath planning for the robot so that it doesn't have to be done manually. I would never be able to do this myself. Can we make that process so fast that that can also be used as a design input? Can that be fast enough that I can design in response to what is constructible by a robot? And finally, we're looking at ways that we can introduce reused and found and irregular material into design space exploration, both because of the impact on climate change and also because we think this is a really interesting and important new design method that reconciles kind of the infinite power of parametric design with the physical reality of available material. So to conclude, I'm really excited about these recent advances in data science and learning, not because of, not for their own sake, but really because I think these are a really powerful way to empower better and more natural links between this systematic design space exploration driven by performance and the need for this flexible, freeform, creative design process driven by humans. And I think the advances in recent digital fabrication technologies can start to make these lightweight structures economical and financially feasible again in all parts of the world. So I think we are going to see a renaissance in the structural revolution, and hopefully we will see many more lightweight structures in the future. Thank you.
Thank you, Caitlin. That's so amazing presentation, and it's also a lot of project we saw the first time we saw it, and we will try to download the software and test it. I think there are several people who have questions. Maybe we can discuss later. So the next presenter is Dr. Alberto Pugnali. He is an architect and a senior lecturer in architecture design at the University of Melbourne, and he is architecture pathway coordinator of Bachelor of Design at MSD. He is also a member of a Bio-Inspiration Research Initiative. In 2007, he won the ISS Hanger Prize, and from 2010 to 2012, he was assistant professor at Aalborg University, DK. He taught as an invited lecturer in China, France, Indonesia, Italy, and the US. He is also a member of International Association for Shell and Special Structures, and he is also at the editorial board of the Nexus Network Journal and the International Journal of Space Structure. So let's welcome Dr. Alberto start his presentation.
Thank you very much, Nick, for the kind introduction. I'd also like to thank the other event organizers and my colleagues. I'm really delighted to be here today to present my work. Please allow me to share my screen. I'm going to put the presentation in full screen mode. Now you should be able to see it. So I would just like to begin by providing you with a little bit of extra background on my research and teaching. I've been working on the computational morphogenesis of shell and spatial structures for almost 15 years. I've also worked on the design history and morphological aspects of reciprocal structures. And what I'm currently doing is writing a book on Dante Bini's inventions, which will be published early next year. As you said, Nick, I've been employed as an academic in different countries, in Italy, Denmark, and Australia, primarily, where I coordinate design studios and construction workshops. How do you get in touch with me? The easiest way would be to visit my website and just drop me an email. On my website, you'll also find many updates on my research and teaching and resources for students and practitioners. So now let's get into it. I've decided to entitle my talk, How Virtual Becomes Real, because I'd like to begin by discussing the master studio I've been running for the last 9 years at the University of Melbourne. What I like is the ambiguity ambiguity in the relationship between the virtual and the real, which can be declined in many different ways, from theory to practice, or conceptual design to construction, or even historical precedent versus emerging design approaches and methods. So first of all, the relationship between the virtual and the real can be understood as the simultaneous use of physical models and numerical tools for finding and optimization. But the virtual and the real can also be seen as two temporal entities which are not necessarily placed in that order. So conceptual design generally inform construction methods, but in my studio, I like to challenge students to familiarize themselves with structural typology and materiality first to find then inspiration for their own designs. It takes generally about 4 weeks to get the students acquainted with these design methods. And in the first week, I start with active bending gridshell. So we use a variety of analog and numerical tools for finding, and the focus is on generating architectural space and at the same time being careful about detailing, therefore resolving the connections to the grounds, for instance, and the bracing system, which are all, in my opinion, essential aspects of what is the final expression of the structure. We use scale models, which are not as accurate as full-scale prototypes, but they're good enough to develop that awareness of real-world issues, which are generally impossible to grasp by only working within the digital domain. The week after, so that would be week 3 of the studio, we moved to pneumatic form finding. And we primarily use rubber sheets and plaster of Paris, or a cleaner technique is using vacuum forming. It's another very challenging exercise, but it's essential to master the potential limits of the system in order to succeed in this case. And I think it's also very important to be able to move across scales to translate structural form into architectural form. You see here the students are sketching speculative ways in which these models can be used. The last challenging exercise we go through before providing the students with a site and a specific design brief is reinterpreting a selection of design precedents. So here's the exercise: is to reconstruct the original shell or the grid shell to familiarize with the form finding and optimization strategies that were used. And by making physical models and preparing the digital files required to laser cut a model, the students realize whether or not construction or fabrication issues inform the design, which is definitely the case here in the courtyard roof of the Smithsonian Museum. There are other design precedents in which geometric forms, for instance, were used. And in that case, the students have to highlight how the use of geometry led to a certain degrees of construction rationality. I'm looking here at the preparation of the concrete formworks for the Kreisky Auditorium, for instance. That's what I like to see from my students. Then there are other cases in which we look at tensile structures. And what I'd like to clarify here is that the work you see on the slide is generally produced within 1 or 2 weeks of studio by a group of 2 to 3 students maximum. Then it's the moment in which we get to week 5 and we provide the students with a clear design brief, something that will allow them to take advantage of large span structures. It could be a wellness center, but it could very well be a swimming pool or a winery. And here is a student project based on the use of minimal surfaces to design the courtyard of a wellness center. But you can also find many other projects in which there is a combination of techniques. So for instance, here we see geometric form that was used for the vaulted ground floor structure, and for finding plus optimization were used for the other shell, again, with a combination of physical models and digital numerical simulations. There are also other cases in which the student doesn't design a shell at all. So here is an example of a branching system, for instance, which was made of clusters of steel columns, optimized to achieve a sense of randomness, let's say, in a space that is covered by a roof tessellated by a very regular grid. So there is that contrast again between the two items. And I've placed this slide here because I'd like to show you what is the final body of work that a single student would produce in the 12 weeks of studio. So there are generally between 4 to 5 boards to illustrate the design proposition, the computational design workflow that was used, and there are generally some details. There is also a variety of physical models that are made throughout the semester at different scales and different levels of resolution. And unfortunately, during the lockdown last year, we had to ditch the physical models entirely, and unfortunately only work within the digital domain. However, we tried to preserve the spirit of the studio. In this case, started, for instance, with the understanding of how hyperbolic paraboloids works architecturally and structurally. Here, the brief was to design a winery in regional Victoria, here in Australia. So there is a degree of construction rationality that is intrinsic in the use of hypers, and that's why we were able to teach the models. And in a way, this is leading to the second part of my presentation, in which I'll discuss a set of other design precedents which I've used as a source of inspiration to develop my own research projects. What I generally do in teaching is also the same approach that I use for my own research. So what you see here is the Church of Longfellow in Italy. It was designed in 1959 and completed in 1965. It's a very impressive composition of hyperbolic paraboloids, and I thought, it would offer an opportunity to challenge parametric design beyond the typical uses in structural design, which are either for shape optimization or thickness optimization. And if we look at the church from the geometrical point of view, it has 2 axes of symmetry. Therefore, you can take a single quarter out to understand its geometry. So if you look at the archival photos on this slide, you can notice that the 4 quarters of the church are also structurally independent from one another in reality. So 1 quarter is made of 4 hypers, and there is a 5th hyper that is used to define the clerestory window. And then there is a concrete frame on top of that to make the system even more complicated, or make it look even more complicated. Of course, it has a structural function. In these archival drawings and models that you see in these slides, there are many different spatial configurations that were explored by the architect, Pino Pizzigoni, but very few of them correspond to the actual building. So that's very curious. The only thing that is recurring, I think it's 3 concepts, which I believe inspired the architect throughout the process. So the very first concept is, of course, having hyperbolic paraboloids. Pizzigoni was truly obsessed by that, and he also wanted to articulate hyperbolic paraboloids in such a way that it would form a twist, a sort of Möbius ring. And the third concept relates to providing shelter, so it's a God's tent. So now we are at the stage in which I said, why don't we parameterize the church so that the invariants of the parametric model refer back to the 3 original design concepts rather than the final geometry? So I wanted to push parametric design to generate new topologies of this church during the structural optimization process, and not simply variations of the same topology by deforming its shape. So we used 8 points to define the edges of the hypers in 1 quarter of the structure, because we preserved the symmetry of the original design. And then, of course, there are only 3 options that remain for the 5th hyper, which defines the clerestory window. And they were chosen randomly every time a new individual was generated in the optimization process. Here you can see a very short video of this optimization process. It was performed using a genetic algorithm, and each individual in the population generated by the GA has a different topology, as you can see. Well, as you would imagine, there is a problem of self-intersection that was taken into account, and also the overall footprint of the building was considered. These were 2 separate penalty functions of the optimization process. And now the most challenging part, which is trying to make sense of the results. Well, we first classified a large variety of configurations obtained according to their mechanical behavior, but we also tried to reconstruct the different geometric features that we found throughout the optimization process. But we didn't really get to the turning point of our understanding of the optimization process until we prepared some hero shots of the interiors. And that's the moment when we realized that many of the optimized results didn't articulate the I-parts generating a twist. Therefore, the concept of the Möbius ring was somewhat lost. And that is the most interesting architectural feature of the original church, if you think about it. We would need now to go back and start from scratch, of course, with a new parametric model that could embed that feature. But this process was extremely valuable nonetheless to understand how much potential there still is in designing nowadays with simple hyperbolic paraboloids, of course, if we consider those I-parts that are trimmed using vertical planes and therefore they got linear edges. Now, I would like to move quickly to the second design precedent I'm using in this presentation. In 2018, I was invited to write an article for a special issue of the ISS journal to celebrate Frei Otto. And I was terrified because Frei Otto's his work on fault finding and structural design is very well documented. And I didn't know exactly how I could develop a new narrative that wasn't written elsewhere. So I decided to develop my narrative from a different angle by focusing on acoustics. It was a way to reinterpret Frei Otto's two-step design method, which was based on the sequential use of a fault-finding model first to literally find structural form, and then a technological model to study the tectonic aspects of the structure and also demonstrate that the initial form that was structurally found could be built. But the reason why I connected Frei Otto and acoustics is primarily based on the retractable umbrellas that he made for the second leg of Pink Floyd's Animal Tour in the US, 1977. Architecturally speaking, I was really amazed by the presence of Mark Fisher's work and Frei Otto's umbrella on the same stage, and at the same time, that generates a quite interesting contrast since Mark Fisher had always joked about his rock stage designs. He used to define, and I'm quoting his own words, the invention of the unnecessary by the unemployable. Whereas for Frei Otto, it was quite the opposite because he stated in an interview that his structures return their attention to the origins, to the necessary, and to the basic principles of life and nature. And another reason why I decided to link Frei Otto with acoustic performance comes from his music pavilion. This one that was constructed for the Federal Garden exhibition in Kassel in 1955. And even if it is a 4-point tent, a very simple design, its purpose was to shelter space for outdoor musical performances. So I thought there must be a connection between acoustic design and Frei Otto, even if that is not very visible in many of the publications I find about Frei Otto. So what I decided to do was to write an article and work on two iconic designs by Frei Otto. The first being the dance pavilion in Cologne, and the second, the set of umbrellas that were later added at the same site. So for this reinterpretation, which is an optimization process, I've considered two different scenarios for the dance pavilion. On the left here, you see that there is a single omnidirectional sound source on the dance floor, while on the right, there are 6 omnidirectional sound sources to preserve rotational symmetry. The dance pavilion is placed at the center of a circular pool, which is white here on the slide, and it's on a small artificial island. It's an open air dance floor and it's covered by a white fabric canopy, which is the tensile structure. There is a tension ring in the center and an alternation of high points and low points at the boundary. The audience area for the purpose of this optimization is located outside of the perimeter of the pool. So the high points of the pavilion are allowed to vary in height, and they can also be moved along the high point center axis to increase or decrease the overall covered area. We use the image source method to evaluate the acoustic response just up to the first order of reflection, and optimization was performed using a multi-objective genetic algorithm. And the two fitness functions were the standard deviation of the sound pressure level, and second, the sound pressure level sum. So you can see here that the optimized solution on the left with one omnidirectional sound source somehow accentuates the original features of the structure by separating even further the high points and the low points. While the best solution on the right is a rather shallow and I would say underwhelming structure from the architectural point of view. But it was very interesting to go through this process to understand the original design and how that could be expanded by using acoustics. I'll just move quickly to the next case study, which are the umbrellas that Fraiotto designed at the same site. In this case, I consider the umbrellas as acoustic devices that are able to reflect sound rays, so they could be rather speculative, this thing considering the fabric that was used. Also, I didn't want it to become a visual obstruction for the audience. In this case, there are 4 design variables for each of the umbrellas: the height, the rotation angle, and the position along the UV coordinates of the audience area. And looking at the results, 2 of the umbrellas have been quite obviously moved to the back of the audience area to help reflect the sound. In the original design, the 5 umbrellas were built with different heights that increase as one moves closer to the stage. And you can see that the same pattern is present in the optimized spatial configuration. So if I have to conclude on this case study, I would say that Fraiotto's 2-step design method can now be synthesized into a single computational workflow, because computationally you can take into account structural form, architectural technology, and acoustic performance at the same time, or even any other performance criteria. So the next case study, the next design precedent or architect in this case I've learned from is Dante Bini and his inventions, which are all based on the use of air. His work is quite unique. What I think is essential here is that he was able to transform a for-finding method into a construction technique. So a PhD student of mine, Alessandro Liuti, was inspired by Dante Bini's work in the development of a construction technique for active bending gridshells. He placed a spherical membrane underneath the flat grid of lights, and he used an Arduino board to monitor the gridshell height and internal pressure of the membrane throughout the erection process. The system was entirely simulated within the digital domain first and analyzed using Abacus. Here you can see the preparation of the spherical membrane, which was made in Milan in collaboration with Professor Alessandro Zanelli. It's a very large spherical membrane of 5.2 meters in diameter. And here you can see the Arduino board with the 2 sensors, the distance sensor and the pressure sensor. And now, in the second part of the video, we are on site in Italy, ready to test the system. So on the slide, you can see the increasing height of the gridshell in white and the internal pressure of the membrane in gray. The footing system was prepared before inflating the membrane, also using 4 rails to guide the gridshell in its target position. You can see the target height has been reached, 3.3 meters. The gridshell is now gently guided into the hinge supports, and then shear blocks and the bracing system are added. So here are some photos that will come about the final prototype that has somehow successfully demonstrated the validity of the construction technique inspired by Dante Bini. So now I've been talking a lot about learning from design precedents. However, the applications that I've presented still belong to the problem-solving paradigm. With a PhD student of mine, who is currently in his 2nd year of the PhD, we've been discussing how to use artificial intelligence to get the computer involved in the process of developing experience from design precedents. So with AI, of course, I'm referring to a specific class of models called artificial neural networks, which can either be used to extract or to generate visual patterns. And with variational autoencoders, we can combine both architectures so that in the first part of the model, the encoder that learns patterns from the given design examples and compresses that information into variables describing a latent space. And the latent space here can be considered as the equivalent of the design space. The second part of the model, the decoder, that learns to construct new data from combining variables of the design of the latent space. So for the application that I'm going to show you, we used IntroVi, which let's say in simple words is a variant of this model architecture. So let's go back to the design precedents. My PhD student constructed this data set of 40 well-known shells designed by Isler, Candela, and many other architects and engineers of the last century. These were designed as 3D models. And this dataset of 3D models was then transformed into two-dimensional depth maps. Through a dataset augmentation strategy, the number of samples was then increased to 4,000 because we always need a very large dataset for the model to develop a form of intelligent behavior. I'm going to skip the training process and the description of the training process to show you the interpolation of the designs generated by the decoder, starting from new samples of the latent space. This is the two-dimensional representation. So the interpolation process generally results in hybrid designs that are ideally placed in between pairs of existing design precedents. So here you can see, if you follow from number 7 to number 17, how Candela's is interpolates with Isler and then going back to Friotto and then the Kresge Auditorium. At the end, we decided to test the ability of the model to interpret design precedents, or I should say at least the footprint of existing designs. So we decided to focus on 3 particular design problems. The first being the generation of a shell roof that interpolates between 2 boundary shapes, the rectangle and the circle. And that's the case of the British Museum, where the AI responded with a design that was fairly similar to the original gridshell shape. The second problem is about designing a shell that can turn a corner, so with this L-shaped plan. And it's interesting to notice how the corner was somehow eliminated by developing a sort of ring around it. The third problem relates to the interpolation between 2 independent circular shells, such as in the case of the Hippo house. And again, this is fairly similar to the original design. But I'm not going to discuss more about these. I'd really like to redirect you to Gabriele Mira's presentation that he gave for a precedent session on Digital Futures Young, where he discussed in detail what he's doing in his PhD. Primarily the 3 aspects he's looking after related to the AI and design creativity, which are expertise, playfulness, and now is getting to work on analogical reasoning. So I'd like to conclude my presentation here. I'm leaving you with this great image of the MSD building and its atrium. That's the building in which I'm working. Thank you very much for listening, and I'm looking forward to discussing with you all at the end. Thank you very much.
Thank you, Alberto. Yeah, thank you for your the great presentation, and good to see your new research projects. So the next presenter is also the final presenter is Professor Mike Xie. Professor Mike Xie is also my PhD supervisor, and he is a distinguished professor at RMIT University in Australia, and where he directed the Center for Innovative Structure and Material, CISM. His team pioneered the evolutionary structure optimization, ESO, and the bidirectional evolutionary structure optimization, BESO methods, which has been used by thousands of engineers and architects around the world to design novel structure, including several landmark buildings. Professor Mike Xie is also a fellow of the Australian Academy of Technology and Engineering. He also received the AMG Michel Medal and the Cronus Rose Innovation Award and the Victoria Prize for Science and Innovation. His team also developed the widely used topology optimization software Amoeba. So let's welcome Professor Mike Xie.
Thank you, Nick. Thank you for the invitation to give a presentation here with distinguished lecturers from around the world. I'm going to talk about the same topic of how to design light and elegant structures from a different perspective of topology optimization. there are actually many different methods for doing topology optimization, but my team developed some very simple techniques. One of the early ones is called evolutionary structural optimization. And the idea is extremely simple. So if you want to design a better structure, you can actually start from any design and do some simple analysis and to see which part of the structure is inefficient. And by gradually removing the inefficient parts, what's left behind would be a better and more efficient structure. And it turns out to be elegant as well in most cases. I'll give you a very simple example to explain the idea of the ESO method. So if we want to design a better structure for a given boundary condition, so we fix one point at the top and apply the gravity, we want to know what would be a best shape to satisfy these given boundary and loading conditions. If we don't know the answer, it doesn't matter. We can start from this square design and divide the design domain into small bits and pieces called finite elements. And through this standard FEA analysis, we would immediately obtain such a stress distribution. When you look at the result, you will find the four corners have very low stress, which indicates that these parts are not efficiently used from the structure point of view. So if they're not necessary or inefficient, we can remove these material step by step, and you will see such a process. So every time we remove the least efficient material, and in doing this simple procedure, you will get a different design from the initial design where you have many different colors on the boundary to a new design where you have a single color. So we are getting a uniform surface stress for the new design. Depends on the design objective, and you can use different rules for removing the material. So the simple concept can actually be used for many different engineering applications. You can use it to design stiffness, or you can control the natural frequency, buffering load, or even contact stresses using the same concept. I'm going to only show you a very small collection of the examples we have done. This is a project I did with my former colleague, Professor Mark Barry, who used to be the executive architect for the Sagrada Familia Basilica in Barcelona. So at that time, Mark was looking for the shapes of these columns on the Passion facade. And he suggested maybe I should use a ESO method to see what kind of shape we would be able to get, start from this very crude engineering joint. So we apply all the loads, and because this structure is made of stone, you want the structure to be in compression. So all we need to do is every step we remove the material with the highest tensile stress, and you will see such a process. And with Mark, we did a lot of analysis of the shapes Gaudi designed for that church, and we found amazing resemblance of what we can find from ESO and what Gaudi designed, and Mark used the parametric digital tools to obtain for the final construction. So on the left-hand side, that's a ESO process of deleting the material with the highest tensile stress. Within a few seconds on the computer, you would get a shape like this. These shapes are almost identical to what you would see in Barcelona in the real cathedral. So although we are using totally different approaches, Gaudi used his hanging models and his observation of nature and derive these forms. We use simple computational process of removing the areas with highest tensile stress. But the design objectives are the same. We want to find a shape which would be most suitable for a material, construction material like stone, and that is good for compression. And we want to use at least as little material as possible. So having the same shape is not a coincidence, because it's purely because we have the same design objective. In this 3D case, say if we want to design 2 columns on a flat surface, and starting from this block, every time we remove the material with the highest tensile stress, and soon we will get 2 columns with branching components at the top. So these shapes are again very similar to what Gaudi designed for the internal major columns inside the basilica. Later on, we developed the improved technique called bidirectional evolutionary structure optimization method, BESO, which Caitlin mentioned earlier. So in addition to removing inefficient material from the structure, we can actually add material to the most critical parts of the structure. And such a bidirectional approach would make the algorithm far more robust and efficient. So I show you a very simple example. Say, if we want to design a bridge type of structure, we fix the 4 bottom corners, put uniformly distributed load on the top, and leave a gap in the middle. We want to know what would be the best shape for such given loading and boundary conditions. The initial design could be very simple, as a beam with 4 columns, and all the rest can be determined by the computer using the simple idea of BESO. So it was start to add material and then remove some of the earlier added material. So if you look at this process, we're not doing the simple local modification. It's not tinkering on the initial design. We actually obtained a completely different structure concept, from a beam and a column to an arch bridge. And in addition to the major arch, we have those branches on the top to make the whole structure to be evenly stressed. Another thing I want to point out is, although we are using mechanical rules, but the result we're getting, it's very organic and it's elegant. So I think this is a reason why BESO method becomes so popular with many architects. And not only can we get efficient structures, we are actually getting elegant structures at the same time. And I show you some of the examples by architects who are using the extended ESO method. And this is one, I think it was built in 2004 in Japan using the extended ESO method. And another famous example of using extended ESO method for the architecture application is this one by Arata Suzuki and Masuro Sasaki and their colleagues. And this one is also has also been built. I think it was completed in 2012. And my team has collaborated with many architects. This one was for a bridge proposal in Suzhou with an architecture firm in Melbourne. This one was done about 18 months ago. We were collaborating with an architecture firm in Shanghai and did this design using the BESO method. And this is the same bridge from a different view. And another footbridge we designed using BESO method is this one for Melbourne. And I'm going to spend a few minutes talking about a topic which Caitlin talked about earlier. That's about the design diversity, because when we talk about structure optimization method, people often think about a unique solution, the global optimum, like this peak at Mount Everest. But when you collaborate with architects, quite often they are asking for a different question. They often would like to have many different designs. So instead of one absolute optimum, maybe we should look for something like this. So this is a scenery in China, in Zhangjiajie. Maybe some of you have been there. So there may not be the absolute peak in any of these mountains, but they are of similar height, but just slightly different forms. So this is what we are looking for in our recent research called how to create diverse and competitive designs without changing loading and boundary conditions. I think Kathleen used a slightly different phrase. She was using diverse and high performance, but the idea is the same. But I'm looking from the topology optimization perspective, and we approach this problem from different strategies. So I'm going to show you some of the work we have done along this line. I give you the motivation behind this. This is a famous image of Professor Philip Yuan's footbridge for DigitalFUTURES. Every year, Philip would build a very impressive bridge in Tongji University, and actually the boundary condition and loading conditions are identical every year because it's on the same site. So the boundary conditions are not changing. The loading conditions are the same, are very similar. Philip would invite 15 famous architects to do the load testing every year. So, and this one, the form for this one, it was actually done using BISO and our Amoeba software. And if we are going to do a new bridge next year, when the border opens, we can actually use the same technique and find a different shape. And we have developed several different techniques to do this kind of diverse designs. The first strategy we have suggested is we can, for every optimization algorithm, you have some parameters for the optimization. By changing the parameters, you can get totally different shapes. So this is a very obvious method to get diverse designs. So this is a very simple example, a cantilever beam. And if we use one parameter in the topology optimization BISO, it's called the filter radius R. And this is a commonly used parameter in topology optimization. R controls the size of the member. So if you have a larger filter radius R, you get bigger members. If you have a small one, so if you change from 4.5 to 1, you get the smaller members. The 5 designs look totally different. But in terms of, if you compare the structure performance, the overall stiffness, they only differ by 1.4%. So they are all structured very efficient, but they are topologically totally different. So this is a kind of outcome we want to achieve. So without sacrificing much of the structural performance, we want to get geometrically different shapes. So this is changing the parameter. The second more sophisticated strategy to get diverse solution is to penalize the existing designs. I go back to this famous design by Asazaki. So for this design, if we use our BISO computer code, you can easily obtain like within 20 minutes, starting from So you have a uniformly distributed load on the top, fix the bottom points, and you evolve it using Bisu method, you will get this outcome. And this is very similar to what Asazaki built in Qatar. But once this kind of spectacular building has been realized, you can't copy it. You can't do something similar. You can't build something similar like this. You have to, next time, you need to do something different. It doesn't mean that you can't use topology optimization for the same situation, because you can penalize what has already been built. So any material which appears in the existing design, you can, in your optimization process, you can artificially weaken this design area. So that's what we have done. So we look at the existing design. Any material which already appeared in the design will be penalized artificially in the algorithm. So we will get a different design by not changing anything in the loading and boundary condition. So these two designs looks considerably different. And their structure performance are not much different. It's only different by 10%. And here is another example of how to penalize the existing design. Say if we design another bridge, the deck is in the middle, without any consideration of existing design, we would get such an outcome. So two parallel trusses and the deck in the middle. But if you want to build something different next time, you can penalize all the existing material in this solution, and you run it again. So next time you run it, and the material in the existing design will be artificially penalized, you will get a different design. So the second design, you can see the two arches are getting closer to each other. So it's merging in the top. And if you want to build a third bridge, you can penalize the previous two designs. So penalize both of these designs, and you run it again, and you will get the third solution, and like this. So you can see the three designs are quite different, but the structure performance are almost the same. They differ by 3%. So instead of producing one design, when you collaborate with architects, you can actually provide 3 different designs for the architect to choose. And the third strategy we have developed is to use the constraint as a design driver, because often we consider constraint as some limitation. Sometimes you can actually use a constraint positively to create some diverse outcome. So this is an example. So in the top arrangement, the material can be applied anywhere. In the bottom, we say we create a gap at the middle, and this is a geometric constraint. We want to use this geometric constraint to drive to obtain a different solution. So you will get two process. The one in the bottom, it needs to have a gap in the middle. And in doing this, we get 2 different designs. And the structure performance, they differ by 14%. The top one is more efficient structurally. But if we are talking about designing a bridge, although the one at the bottom is structurally slightly less efficient, but it's actually more like a bridge. It satisfies the functional requirement of a bridge more appropriately. The next strategy is we can specify some non-design domains in the structure. So this cantilever beam. If you don't have any constraint, you will get this design. Sometimes certain areas you can't can't change or can't modify. So you can have this A, which should always be there, B, C, and by specifying these non-design domains, you get different design outcomes. And their structure performance, the 4 solutions are all very close to each other. And you can also artificially make some regions of the design domain weaker. So you can say, I want the structure to have more material to the upper half. So you would get 2 new solutions. And these 3 designs have quite different shapes, but they're actually structurally equally, or the structurally, they're all quite efficient. And the last strategy we have developed is we can introduce some randomness into the optimization process. A simple one is you can artificially drill some holes for the initial design. These holes can be filled later on if they are important, but we put it there initially just to put some perturbation to change the evolutionary path of the optimization. So because there's some random holes in the initial design, so the optimization history has been slightly changed. But although the 2 shapes are totally different, but their structure performance only differ by 2%. So my team has implemented all these techniques into Rhino Grasshopper plugin called Amoeba, and this is has been widely used by many architects, and it's all based on cloud computing. So we have a server in the US and another server in China running all the models from many users from around the world. So I'm going to show you some of the results, some of the models by students who used Amoeba software. So this is some of the furniture my students have designed using Amoeba, and this one we have actually 3D printed two of these. This is fully functional. It's not a small model. You can put 5 people on it. It's very strong, and we actually won some awards for this 3D printed chair designed by Amoeba. If you come to Melbourne, you are most welcome to visit me. And in my office, all my chairs and we have all the desks, all designed by Amoeba and 3D printed or laser cut and made these furnitures. These were from 2 undergraduate students who learned Amoeba for half a day, and the next day they designed a high heel shoes for themselves and 3D printed. And this is another student's work using Amoeba to design a wooden pavilion. This clever 3 young students redesigned the Eiffel Tower using Amoeba software. It's incredible what they did within a few days of using Amoeba. They didn't have any knowledge about topology optimization before they started the workshop with Nick and myself. This is another undergraduate student work using Amoeba to design a student activity center. And this one, Art Museum, it's by the same 3rd-year undergraduate student. I'm going to spend the last few minutes talk about our latest work. So most architects are familiar with the root surface, which is made of straight lines. And recently we have been considering using the elastic curve as a new way to generate complex shapes. So elastic curve is simply made of bending a slender rod. When you bend the rod elastically, you will get naturally this elastic curve. And there's a formula to define this. If you look at this image here, on the left-hand side, this blue image, these are the traditional root surface. So this surface is made of straight lines. These are called the ruling. And we have been thinking, if we replace these straight lines with the elastic curve, this red curve, we can use this curve to generate far more interesting shapes. So we actually made up a new term called elastical root surface. And we try to use this new concept for architectural form definition, because elastic curves can be parametrically the curves can be parametrically and accurately designed every point. So it's not a totally free form. Every point on the elastical root surface is parametrically designed, and we know exactly the coordinates of every point on this surface. Sounds like a simple idea, but we played with it. We found that using this simple idea, we can generate a rich and diverse form of shapes. So the left-hand side, all the blue ones are the root surface with straight lines. By replacing the straight lines with the elastic curve and sweeping through, you can see all these orange or red shape. These are the elastical root surface we have generated by simply changing the straight rod into an elastically bent curve. And we can even make a kinetic elastic surface to make the whole surface moving. So for the top row, we are moving this purple line in the horizontal plane, and the whole thing would start to dance. Some of you may have seen Calatrava's wave sculpture. This is far more, the shape is far more sophisticated than the straight rods. And the next one is we can rotate the purple line and to make the whole surface to move. And we can also use high order elastic root curves. So this is the second order. So it curved twice here, and this is the third order. And by using high order elastic root surface, we can generate even more interesting shapes. So to finish, I show you a short movie about our current work on the what we call elastical root surface. Thank you very much.
Thank you, Professor Xie, for the impressive presentation as usual. So thanks everyone for the amazing presentation. If I can ask all of the presenters put on your camera, and we can move to our next stage of the discussion. So Professor Maxi, you can stop sharing your screen.
Yeah, yeah.
Yeah, so thanks everyone. Also, I saw Professor Pavilion also join us for the discussion. Yeah, so part of the reason I called all of you here is you are the expert in the structure and architecture, and also all the presenters are part of the members of International Association for Shell and Special Structures. And some of you will have met in Barcelona 2019, and some of you will met online. So maybe I would like to kick off the discussion first. Also, you are also welcome to propose your questions to each other. So the first question I'm interested in is, most of you both have the architecture and engineering background. And so I would like to know how you shift yourself from architecture to engineering, structural engineering fields, or the way around. Because I did my bachelor and master in architecture, but I studied the structural engineering and in the School of Engineering at MIT. So and how can we use the computational design method to balance the architecture aesthetics and the structural performance? I think it's also part of my research topic. So who wanna start this discussion?
I'm happy to give an answer. I think it's a great question. In many parts of the world, there aren't places where you can study simultaneously structural engineering and architecture. They're almost always separated. In my own education, it was honestly quite a lot of whiplash going back and forth between these two worlds because they are so different and often are so isolated from each other. I think there are a few places in the world where architecture and structural engineering are taught in a more integrated way. I'm thinking of Japan, Belgium, Spain. I'm sure there are others. And I think, to me, that is obviously the correct model. That's what we're trying to create at MIT for our students. And I think we're seeing that emerge in many other parts of the world through all of you. And I think that's absolutely wonderful. It's really, really hard to study these two things separately and then think about how to synthesize them all by yourself. Being in an environment where the synthesis is part of the discussion, you're not just talking about two fundamentals in two different fields. But to me, that's really, really important to educate more people in this way.
Thank you, Caitlin, for the answer. Anyone have the answer for my question?
Yeah, I don't mind adding something on that. I come from a background, Italian background, in which this model is very similar to Spain, if you wish, but the place in which I'm right now, the University of Melbourne, is not following this model. So most of my students don't have the mathematical and technical background to become engineers unless they develop a double major. They take a double major and then get a double master's at the end. So it's quite time consuming. I would say that primarily I consider myself an architect, and but I like to learn from engineers' methods and rigor in the way scientific research is carried out. I think that's the main important thing. At the same time, it's always, I think most of the things we've seen here in the talks today, it's not too much about the technicalities, but it's about finding the right idea. So that's what we should probably learn from architects. It's always about finding the right way to innovate within a field, and then the technical aspects will follow somehow. But in order to do that, you have to have that background to develop the right idea, because it's always a forth and back, as I said also in my presentation, between, finding the right source of inspiration and then generate idea. You cannot generate ideas unless you have a deep understanding of what you're talking about. But I do like the rigor and the method of the engineers. I think that's something that is quite missing in the architecture schools that don't have that polytechnic background.
Yeah. Thank you, Alberto.
Hi, this is Philip. Yeah, I want to say something.
Yeah.
It's a great event and fabulous people here. I think it's a top level talk on the light architecture. So I think it's, from a pedagogy perspective, it's really interesting to talk about the education system, because normally we separate architecture design with a structural engineer school. So actually a lot of my background is actually I'm an architect, and I have a lot collaboration with very famous and very top level structural engineer like Mike Xie and like Philip Block and people from Europe, a lot of partners in different projects with them. I think I'm learning a lot from the process of how they understand architecture from a quite different perspective. Actually, for example, Method and Pedagogy, you're talking about the graphic statics, especially from three-dimensional form finding, and that is actually give us a new methodology, a new perspective to understand how to generate a certain kind of family of form, which can base on this kind of very special graphic static analysis and give a very interesting solution, actually, which is not just one optimum solution, actually, which is a family of forms can put on table for the architects to make some decision, and actually which can integrate with some different consciousness or imagination from the architect perspective. I think that is a new collaboration between the machine and human. And the machine is not just a machine, but this kind of toolbox, which developed by different kind of team, different kind of people. So this is totally open a new a working methodology or new paradigm, which is totally not only based on the human imagination, and the design process should invite this kind of toolbox machine intelligence, which can help us to generate different kind of material intelligence based on the collaboration between the human and the machine. So I think that's a new age. We should think about rethinking about the design and thinking process. And it's really important to introduce the structural engineer, especially the structure mechanics knowledge into the structural engineer and architecture design process. So I think this is really important to discuss about education and how we reorganize our education system. So I think no matter you're learning from the structural engineer or from architect, it's very important right now to start understand each other, to set up new collaboration, not only with the people, but you should collaborate with different machine, different toolbox. So that is probably a very meaningful milestone for this talk, because we have a lot of audience, maybe more than 2,000 audience in China on Bilibili. They listen to this special talk. I think that is really meaningful for a lot of the big army architect here. They can understand that is totally a new horizon, a new milestone we should set up for the future of design. So thank you for all the speakers here today.
Maybe I'll follow up on that. Yes, I also agree with all these comments. What I would say is that my journey to the field of architectural engineering was a little bit different, because I was trained first as an engineer, and because of the passion that I had, I basically left engineering and went to architecture school. And once I finished architecture school, I realized that still there was not a clear connection between architecture and engineering. So that's why I basically tried to develop a research that could bridge that gap. But what I can say for today's educational tools is that the abundance of these tools, the available softwares and plugins, that makes it, I would say, more accessible for many students, both from engineering and architecture, in order to learn and apply to design. And frankly speaking, this is not, design has so many different parameters and basically objectives. And optimization and form finding and structural systems and mechanics can be one of those, but quite necessary, right? So based on my interaction with architects and designers who sometimes try to reject optimization tools, what I realized is that maybe optimization is not always desired for architects, but rather approaching it from a different perspective, that they need to understand the force flow in their design, and they basically respect the mechanics of working with material. That should come first. And many of the methods that has been explained in this session can definitely be used for basically for that part of communication, and trying to basically enable them to understand the properties of their design. And then in the next step, they can decide whether they would like to work with an optimized solution or not. But that is quite key in order to bridge that gap. Otherwise, no matter what optimized solution, variety of optimized solution we provide for designers, many of them might actually reject that because of the deterministic approach that optimization might actually have with respect to design.
Yeah, following up on this, I guess it was quite evident today from all the talks how much important is actually this topic of bringing together structures and architecture, using structural principles as driver of the design. And to a certain extent, we saw also today how much actually going into this approach is really triggering the creativity of the designer. So the structural principle should not be really seen as, or structure in general, as an obstacle to the creativity in architecture, but rather as a driver, a support. And it was very amazing to see in all the talks today the fantastic results of very often developed by students that are playing with these tools that are developed, and they understand the certain points, what is the relevance of thinking with a structural mind, but not forgetting about the question of architectural quality. And all the designs that we saw, especially in the last presentation, was fascinating to see all the results developed by the students of Professor Xe. It's very interesting to see how much the students, they can really take advantage of all the opportunities of these tools, often even much more than the researchers that are developing the tools themselves. So it's really, for me, the most relevant point is the fact that these tools and these approaches are really triggering the creativity of the designers. And this is showing how much these technical aspects are not just staying on a technical domain, but they are really embracing the topic of architectural quality.
Yeah, I agree. And like about to talk about, in Australia, the education in architecture we don't need to learn the mathematics or the structure. So it's quite challenging for me to start my PhD in Professor Max's lab at the beginning of my PhD study. So maybe Professor Max can talk something about your challenge to supervise.
I'm a structural engineer by background, but I really enjoy working with many architects like Professor Pavilion. We collaborated on many real projects, and it's always interesting talking to someone in a different discipline. The work on the diverse designs, it's actually motivated by a lot of requirements and questions by architects, because when in the first 10 years when I'm working on topology optimization, when I go to conference, the colleagues often ask, "Oh, can you guarantee your solution is the unique global optimum?" So my people in my field, they're obsessed about the global optimum, the unique, absolute best solution. But these things are, when you talk to architects, they have totally different mindset. They say, "Oh, can you give me 10 different solutions so I can satisfy my other architectural requirements?" So that different mindset is actually helping for frame the new research questions and to develop your techniques to be practically more useful.
Yes, I want to follow Maxi. I think we have a long-term collaboration in the past, I think over the past 7 years, right? Yeah. And especially working on very practical projects. Actually, we have a lot of discussion, and architects normally want to challenge the structural engineer because we don't believe the optimum is the best. Because sometimes from a structure perspective, the global optimum is the only best solution, but actually sometimes the architects would need to balance different multi-objective motivation, because sometimes, and not just gravity, we have some other aesthetics or some like environmental performance motivation, or some special behavior performance we need to take in account in the design process. So sometimes we want to hidden the structure logics, and we want to set up some more cultural aspects on architecture. So all this kind of feedback gives different kind of solutions. So that's, I appreciate Kathleen in your lecture. Several diagram is super impressive, because they're talking about the local optimum, which is like a different stadium. You can find different mapping the diagrams, find different solutions of different structure system. That is actually really a good balance. Architecture and the structure engineer, I think that is extremely important. I want to check your paper on that. So I think it's quite impressive today. I really learned a lot. And a second question is about the skill. Normally, the solution, for example, from BSO, you can generate certain kind of form, but sometimes a chair is different to a bridge, because the material performance really matters, the scale. You need to take into account the material performance, and sometimes the tectonics means the gravity is not normally just like compression. It's also should take in consider about the different kind of other, like bending performance, different kind of other material performance situation. And sometimes, like Newrich mentioned, the yin gang is different to a human being. Why the human being, the scale of the human is a human, because the bone actually have their material performance. So based on that, I think the solution of the optimum should take in account of the skill. So for architects, it's extremely important when we design a bridge or we design a super high-rise building. The tectonics means certain kind. We need to set up the tessellation, set up the unit or component scale, and how to make calculation on this kind of discrete system, discrete structure prefab system. So that, because we're working on a lot of a very big scale architecture, I think the concept of this kind of optimum is important, but in the real situation, I think the local optimum is really important, firstly. And secondly, I think we need to balance the scale. And based on the scale, I want to hear different feedback from all the speakers. If you have any understanding on that, it would be appreciated.
Great point, Philip. This is really, really important, particularly working with form finding techniques. It's quite important to know what are your design loads, right? So, for instance, you compared I remember an image from Professor Shi's presentation that they're showing, yes, the bridge versus the shoe, and also the Eiffel Tower, right? So as you brought up, sometimes the applied loads are significantly higher than the self-weight of the system, right? So that is the driving force for your design. For instance, the wind load for the design of the Eiffel Tower, that was the dominant load case, whereas the self-weight, maybe it was secondary. But sometimes when you're designing, for instance, compression only shell structures, there the self-weight is the driver and basically gets you deformed. That any other load case in that scenario might be significantly lower than the self-weight, right? So understanding where the self-weight applies, where the dominant load in the coming from the environment applies, I would say that is quite necessary in any approach that has been presented here today that you want to take as a form finding. So again, just to conclude, it's really hard to find a single solution that can address both force systems. So we need to be selective in that regard. Even the example that you mentioned from the human bone, right? So it happens, this form finding or this optimization happens in multi-scale or at a fractal level. So if you look at for instance, the skeleton of a human, that has been optimized for the gravitational force. That is a global force applied to that system, and it's been optimized for that. But if you take a section through the bone, then you will see that, oh yeah, the bone has been optimized for any kind of bending force that might be applied from the side. So that distributes the trajectory of the material to withstand any bending that might actually cause fracture in the opposite direction of the gravity. So again, this is really, really interesting discussion, because we are not only looking at the global optimization, because then you need to take a microscope or a magnifier and then look at that global solution and see what is happening within the members of the global for any other load scenario, which might not be the design load case.
Good. I think today is another very interesting aspect. Actually, most of you actually implement the machine learning in the graphic statics research process, or the searching the different kind of solutions based on the big data and different diagrams, for example. So I want to say something to predict the future research in this field, how the artificial intelligence will influence the research. The first question. Secondly, is that aspects is still a problem, because after we implement this kind of tools, a toolbox or the machine learning, that is like a working flow, is that limit our imagination, because normally is which lead us to certain kind of style, because which help us to find different solution, which normally based on the machine toolbox, that is we set up based on different kind of rational logics. But sometimes when the designers collaborate with the engineers, sometimes this irrational design process will give us some special unreasonable solution. So I don't know if you can make clarify the difference between the artificial intelligence form finding with the human formation, imagination, design process.
Yeah, I think that's a really important question, and it's one we hear a lot. I think there's a lot of worry legitimately about artificial intelligence as something that will reduce the involvements of humans and the creative influences of humans in design. I will say, however, that's basically the same worry that people have about optimization. So, and there's a very similar argument, right? So optimization is insufficient because we can't really define an objective function appropriately. Machine learning can be really problematic if we're training on insufficient or bad data, right? It's a very similar thing. What if we're learning about, you know, how to design a really bad building, we build an algorithm that can generate bad buildings? That's certainly worrying. I think it's really important to keep those concerns in mind as we develop these methods. From what I've seen here, I think none of us are trying to do that. We're trying to use recent learning methods to amplify ideas that we've already had and to make these methods better. Because unfortunately, I think we're all true believers in these methods, but they're not used widely right now in practice. And I think my sense is that some of these advances in learning can help with that, both in terms of the scale of the data that we can handle, broadening the applicability of these methods to new typologies, and also, as I said, really making things faster so that it's easier for someone to use who's working on a really tight time scale on a lot of projects. Designing an airplane has a different time scale than designing a building, and so architects really need interactive, fast tools that are responsive to their creative method, and I think learning is really powerful for that problem.
If I can add on that, I fully agree with what you're saying, Kathleen. I really think that there is a similar argument that was raised years ago on optimization, and it's now coming back. Unfortunately, AI can have a very limited experience of what can be achieved, because it's only about the training data set that's being provided to those models. I would also say that at the moment, at least in the presentation that I gave, we were talking about a very specific knowledge domain. I think it would be in the future, I think one of the biggest challenges would be to be able to move across different knowledge domains. That would be one of the things that we as humans do quite naturally, but it's almost impossible to do with automation, because generally you work within a design space that sits within a knowledge domain. But with artificial neural network, you can definitely do this step, so that to try to tackle analogical reasoning. I think that would be one of the objectives of my PhD student, even if we're not quite there at this stage. But I believe that is the key, at least for us, in next year or so.
Yes, I agree. Also, I think these tools, especially machine learning, should be always be considered as a way to support the design rather than try to substitute the human designer. In a way that this tool actually, if they are used in the proper way, they can indeed open us new horizon in what can be designed by the human designer by bringing in new ideas into the design process. And then clearly it depends quite a lot on in which phase of the design these tools are used. And each phase would require a different way how to use these tools themselves. So when we are in the conceptual phase of the design, we don't want to narrow down the design space, but rather to open it up and then support the human designer to navigate into this design space. So I really see the use of machine learning as a way to support, especially the conceptual phase of the design. And when it comes to an advanced phase as well, but clearly the tool would be used in a different way. So I totally agree with what has been said before, and I really see this all in all, also in the talks today, we really make use of these tools in this more creative way, rather than trying to narrow down and find this impossible optimal solution that, as we said, that doesn't really exist.
Yes, that's really impressive. Please.
I just wanted to add one more thing to that thing. I totally agree that machine learning can be used to broaden the palette of design for architects and designers and engineers, for sure. There's another aspect of machine learning that should not be basically underestimated, and that's I myself at the beginning I was really doubtful about the machine learning, the use of machine learning in design, and the lost authorship of architects and designers in that process. But then later I realized that machine learning can actually be used to decipher certain patterns existing in really complex systems that maybe will take, I believe, Caitlin, you pointed out this in your presentation also, that will take years for instance, human to understand that, particularly if you're dealing with natural phenomena and you want to learn from that and really apply it. So this is, machine learning would actually help you to decipher that fast and maybe categorize that idea. But then after receiving the result from machine learning, you as a designer would process that data and learn how to use that data for a new design, rather than just using directly the outcome of machine learning, but understanding what is happening and basically applying it based on your authorship. So I still, from that perspective, I believe it's going to be really, really important in the future.
So Neil, do you have any question you want to put forward? Because Neil is right now set up a lot of discussion on the artificial intelligence. But actually, I want to challenge Neil because you normally you want to address artificial intelligence in the stylistic or the like formalism design process. Maybe that is totally changed the paradigm of the thinking or imagination process of design. But actually today, I think that opened another field, especially in the structure design, which is machine learning or the artificial intelligence, really important to make analysis or give different kind of pattern from the structure diagrams. Actually, that is a very important solution or a lot of people make research on that. I think I want to hear your voice. What's your comments on that?
Oh, Philip, don't get me wrong. I'm very skeptical of any discussion about style. Absolutely, completely. And I don't think actually that AI is about style either. It's about feature recognition, I think, detection and so on. But I would just simply say that, I think that actually I wasn't so much aware of some of the machine learning work that's been going on. I'm aware of topological optimization, but that's kind of good old-fashioned AI, and to have machine learning coming into it is really quite important. Back in 2002-3, I think it was, when I was at the University of Bath, we, together with David Turnbull and Chris Williams, we had a conference called Digital Tectonics, where we tried to bring together these two domains. Incidentally, one of the students in the audience was someone called Akim Mengiz that day. And I think there's another conference that needs to be suggested about the use of machine learning in terms of structures and architecture. And I think it's really, today it was a fantastic presentation. I want to thank all the presenters, because this was, in terms of what we're doing, this is such an important session, because it's a resource that's available for free for anyone to look at anywhere in the world, and what Philip and I have been trying to do is to kind of break down the walls of the classroom and also to challenge the idea that educational ideas are only available to those who can afford to go to the AA and elsewhere. We've now got a resources available for free for everyone in the world, and it was a fantastic resource today. But I think this is pretty kind of, in a sense, this is in a work in progress. I was really impressed by that, and I want to find out more about the machine learning side of things. I absolutely think that is an important way to go. And for me, it might be dealing primarily with representational tools when you're using GANs and things, but it's about the process and how we can use that process and harness it in interesting kind of ways. I'm particularly interested in the question about creativity and whether that is an issue or not. So I just want to thank you. We should really think about having a separate session on machine learning and structural performance and so on in the future after our big event over the summer. And just to mention that next week we will be having a whole discussion, Philip and I, about the Inclusive Futures event over the summer. Yeah, but no, style is, I'm definitely against style, and those who see the world in terms of style, I think that's I think anybody who is working in a kind of engineering or even architectural viewpoint doesn't think about style. From the outside, maybe historical commentators might think about it in terms of style, but I don't think anyone who's a designer really thinks in terms of style.
Okay. Yeah. Thank you, Neil. Thank you, Philip. So I think we are almost run out of time, and thanks everyone to join this session. And also, it's very late for Professor McShane and Alberto in Melbourne. It's almost 2:40 a.m. in the morning. So thank you, everyone. And hopefully we can see each other in next ISS conference. So also in Digital Future in person. Okay. Thank you, everyone.
Thank you. Thank you, everyone.
Thank you.
Nice to see
Thank you very much.
Thank you all.
Bye-bye.
Thanks for the invite. Thank you very much. Bye-bye.
Bye.
Oh,
Thank you, everyone.